Yeah, so he's at the Sorbonne University, and this is really one of the top universities in France, of course. And he's at a very, very important lab as well there. And we are very happy to have him share some of his work with us here. Of course, I met Sidi through SIMPA. We applied for SIMPA to organize the first SIMPA school in Ghana. And this will be done next year in numerical PDEs and analysis. And so we'll also inform members about it who want to participate. And we were successful in this application. And so SIMPA is going to be held here in Ghana next year. And I met him through the application because together with him, we did the application for this call. So he's going to talk about, and CD is actually, has written several books in numerics of PDEs and has a lot of collaborators as well, all over Paris and France and Switzerland and many places. And he actually is almost every year now, for some years now, has been visiting Benin for some weeks or a month or so every year, and to teach students there as well, and to share his experience with them there as well, which I found it very interesting as well. And so today, we are very happy to have Sidi-Mahmoud KABER with us, and he's going to talk on parallel approximation of the matrix exponential. So thank you, Sidi, for agreeing to share with us. Thank you very much, and you can go ahead.
My pleasure. Thank you very much for this introduction. I'm happy to give this talk in your seminar, and also I'm happy to have see that our proposal was accepted in SIMPA, and the first SIMPA school will be held next year in Ghana. I'll be happy to visit your country and meet people then, students and researchers and professors. As you said, I'm in charge of a program of cooperation between my university and University of Benin, and I go there each year for lectures at the master level. Good. So I'm talking about parallel approximation of the matrix exponential.
Boring.
Okay. Let me just start telling you why I'm interested in this problem. It's mainly because of the use of parallel computing. Yeah, as you may know, or certainly know, parallel computing is not new, but it seems strategic issue for programming, and this is the main reason for why I'm interested in computation of the matrix exponential. So parallelization is another story in numerical analysis, especially in space direction. So that makes sense if you have to compute to solve a PDE or differential equation on a domain. It makes sense to divide the domain and solve the same PDE on each subdomain, which seems to be easier to do, and then do some correction, some exchange of information from the subdomains and iterate this process. This is what is called domain decomposition method. It's very, the famous Schwarz algorithm is a very good illustration of this. If you really don't know what it's about, let me explain a little bit. Here you have to solve an equation on this domain, 01. So this domain is, let's say, a large domain, and you subdivide this domain. You take two parts, this one and this one, and there is an overlap. And on each of these subdomain or subintervals, you solve the problem. The problem was just a second order problem. So if you solve the problem is in, let's say, in the left domain, you get a solution. Yes. Okay. The value you obtain at this point gives you a new boundary condition to solve the problem on all this domain. Okay. Let me explain here. So at the beginning, you know that just two boundary conditions for your solution. You can guess one value. I don't know which one, but let's say let's pick a value here, solve the problem in this region, this problem, we get this solution. With this solution, this solution gives us a new boundary condition at this point, and we can solve the problem because we have two boundary conditions. Then this new problem will make available a new boundary value here to solve the problem, to be able to solve the problem on the left interval, and so on. At the end, you obtain the solution. So this is parallelization in space direction, and it's very easy to understand what it's about. But this is not only the only way to make parallelization. Parallelization in time also exists. It's a little bit complicated to understand at first glance, because you see that the solution at time t depend on the earlier solution, and it seems strange to do parallelization in time. But parallelization in time exists. There are many techniques. Since I started a little bit later than previously scheduled, I will not talk talk too much about this, what is called the parallel method, and let you consult this excellent reference on parallelization in time. Okay, so I'm interested in parallelization in time. What's the link between parallelization in time and the exponential of a matrix? This is the subject of my talk. So here is the outline. The motivation, why this work, approximation of the metric exponential, and before that we'll talk about approximation of the exponential function, and the last section is devoted to the application of this matrix exponential. Okay, of course I will do some remarks at the end. This is joint work with people from Paris here, Frédéric Hecht from Sorbonne University, Alain Plagne from École Polytechnique, Julien Salomon from INRIA, and Lucas Perrin, he's a doctorate, he's doing a PhD with Julien Salomon. So let's consider this ODE. You have a linear part of the equation, and I put all the non-linear terms in this function called n as non-linear. So this may be the equation you want to solve, but it could be also the linearization of the non-linear equation you are interested in. Okay, so integration, the Duhamel formula tells you that u is exponential a applied to the initial value of u plus some integral involving the non-linear terms. The k idea in what is called exponential integrators is the following. It's we try to compute exactly this part and do the best we can do for the nonlinear part. This is the main idea. Okay, exactly means, of course, as precisely as possible. And you see here two things. I boxed two things. One of them is the exponential of the matrix, the exponential operator. And the other is the action of this exponential on a vector u. So there are two problems. The first one is to compute the exponential. The second one is the action of an exponential on a vector without computing the exponential itself. And usually in numerical analysis, in numerical programs, codes, numerical algorithm, what happens? I have a message and sorry, I have to. I have to share again the screen. I'm sorry, something wrong happens. I don't know why. I don't know why. So this is my. Oh, good. Okay. So the most important thing is to be able to compute the action of the matrix operator, the exponential matrix operator on vectors. So let's forget about the nonlinear part and focus absolutely on the linear problem. So the linear problem is the following. I want to solve u. Right? Sorry, I have a problem. Okay, that's okay. Let's solve this problem. This is a very simple problem. We know exactly the solution, but it's very, very hard to compute the solution. That's why people use the famous explicit Euler scheme. From here, you write u at time m plus 1 minus u at times m divided by the step is a at u at time m. You can also use much more complicated scheme. Let's say the Runge-Kutta schemes. And you see that all these schemes, these explicit schemes, in all these explicit schemes, you go from um to um plus 1 by multiplying this by some matrix or some operators. And this is exactly a way to mimic, to reproduce another formulation of the exact formula. So the exact formula, this is semi-group, the exact formula is, so I wrote this slide thinking that many people do not know that when they use numerical schemes, behind this is really an approximation of the exponential. And you see here, for the Euler scheme, you have for the two schemes, you have just the Taylor series of the exponential. Okay. Now, if you use an implicit scheme, what happens? Let me. So you have the same problem, linear. A doesn't depend on T, of course. This is a solution. An implicit Euler scheme will say that the derivative is equal to the value of function the right-hand side at em plus 1. This means that identity minus HA um plus 1 is um. So you go from um to m plus 1 by multiplying by this inverse. Of course, h should be small enough, and you go from um to um plus 1 by this operation. The Crank-Nicolson scheme is also an implicit scheme. It you can write it this way if all these expression have, if the matrix is invertible, so you have HA, and here I plus h over 2a times um. And what's the difference between this implicit and explicit scheme? It's just here you have not the Taylor series of the exponential, but a rational approximation of the exponential. And I will indeed use rational approximation to compute the exponential of a matrix. Before that, let's see how to approximate the exponential function in the complex plane. This is a very simple and you cannot imagine much simpler idea. It's the following: exponential z is 1 over exponential minus z, and I approximate this by 1 over the Taylor series truncated at order n. Okay, that's very simple. So what are the properties of this Rn? So here it's just a plot of exponential, the Taylor exponent truncation, and the rational truncation to show that for z negative, it has sense to do this approximation because exponential z goes to 0 and 1 over the Taylor expansion goes to 0 too. So you will see that the half axis x negative has very specific role in these problems. Okay. So what I wrote here is just a very simple case of the Paddy approximant of the exponential. The Paddy approximation of approximate of the exponential. Also, for whom who don't know what is Paddy approximation, is just an approximation near the origin. At 0, you want p over q be an approximation of your function f at 0. And what means approximation? It means that p minus q times f has a Taylor series that starts from, let's say, ck x to the k for k larger than some capital K, and you choose this capital K as large as possible. So it's n plus m or n plus m plus 1, something like that. Okay, this is Paddy approximation. So for the exponential, the Paddy approximation are explicitly known. Sorry, and this is it's easy to see that the approximation I will use here is just a Paddy approximation. So everything you know about Paddy approximation is useful for us to understand the approximation properties of this rational function. It is also, of course, a rational function, and you can also look at in the literature in approximation theory what we know about approximation of regular functions, let's say continuous functions, something like on by rational functions. So they are very impressive results. Let's call EMN the error of best approximation in uniform norm for a given for the exponential. You have an exponential, you do an approximation by rational function R that belong to what I denote here P sub mn, which is rational function of numerator of degree m, a denominator of degree n, and you take the uniform norm. So it's a min-max problem, and it is proven that the best approximation of function decreases very, very rapidly to 0 as the degrees of numerator and denominator goes to infinity. So we'll have absolutely no problem for for okay. Just tell you that this is obtained by the best approximation of the exponential, and of course my function has there's no reason for this function to be the best approximation. But the best approximation, best rational approximation, are usually hard to compute. And there is a please. I'm sorry. Please shut off your microphone if you don't have a question to ask. Thank you. Merci. Okay. So there are some theoretical results on the approximation by rational on rational approximation, but I'm interested in very specific. And there is a celebrated paper by Varga, Enardus, and Cody. This one. They are at the same time a paper known in approximation community because it gives a very precise rate of convergence, but also they want to use this rational approximation to solve PDEs. So this is exactly what I have in mind, to solve PDEs. And it's very easy, it's very simple to derive this approximation. They also show that the error decreases asymptotically, has asymptotically geometric convergence. It means that they prove that the error decreases like C to the power n, but they didn't compute C exactly, but they said that they prove that C is less than 1/2. And later in this paper, Schwanhage showed that C is 1/3, but 1/2 is very okay for me. Okay, so what can we do? What can we say? What do we have proven about this? About the error, if you plot the error, I did it here, the difference between Rn, which is the rational approximation. I recall you that this is the Taylor series truncated at order n, evaluated at minus x. You compute the x. Okay, so the shape is exactly what you see here. At 0, it's 0. It had a bump here and goes to the real exponential. And what we can prove, it really not very important in the computation, but it's always a good idea to do fine analysis if we can do it. So what we can do, what we can show that this maximum value decreases very, very quickly, but this was exactly what Varga and Kotor said before. What we can say about this extrema here, it moves like big O or capital big O of n. Okay, so in any case, the maximum here decreases very fast. Okay, that's what you have in mind. So let's, if you want to see what it looks like, even in the complex plane. Okay, I'm sorry, I have to really go fast to give you the main idea. So the idea now is the following: we do a partial fraction decomposition of this function, which is this one. Okay, so this is easy to do. These are the zeros of all the opposite of the zeros of Pn. Each of these coefficients is given by this formula. These zeros of the truncated series of the exponential are very well documented in by people from analysis or approximation theory. They have nothing to do with numerics. And you can find in many references that, for example, they cannot be too close each other for every n. So I was interested in this equation because of the computation of AK. You have at the denominator the product of all these differences, and it's normal to say how be careful. Maybe this difference is too small. This will never be the case. I plot here some of these AK, but concerning the zeros themselves, that are the poles or the opposite of the poles of our approximation, what do you know? Sorry, I forgot to write in the value of n, but you see that this is one value, one other value. So they go to the infinity. This is normal because the exponential has no singularity. So they go to infinity, and we know exactly how they go to infinity. This is a famous work by KABER, and he proves that the moves like capital in numerical notation. We'll say that every zero is a capital O of n. And he shows something interesting about the limit of this normalized zero. They all collapse into this curve. So what is important for me for numerical purposes is just this, to see where are the zeros and where how they go to the to infinity. Okay. Now there is something very important if you are interested in floating point arithmetic or numerical arithmetic or numerical implementation. Exponential x minus. So this is the exponential. This is what we use to approximate the exponential. This is exactly what is written here. From a mathematical point of view, this is just the fractional decomposition of our approximation. So this should be zero. From a mathematical point of view, this is absolutely zero. Okay. From a real point of view, floating point arithmetic point of view, this may be not zero. So you have to exactly see what how large it is E3. And also the zeros are not known explicitly. Even if we don't know a lot about these zeros of the exponential or the truncation of the exponential, you have to compute them using a program. Okay, so there is a lot of things to do to say here in this at this point, but I will not talk about this. I will just show how our method can be used. Okay, if you are interested in, there is a reference, a preprint. This is a preprint. It's submitted, not published now. Okay, so now how to go from the scalar approximation to the metric approximation. Many methods exist to compute the exponential of matrix. Everyone knows that if the matrix is diagonalizable, you have to, it's easy to compute the exponential. But from numerical point of view, it's no, forget diagonalization of a big matrix. That's it's not a solution, okay? Truncated Taylor series also, this is also an idea to compute the exponential. You can say, I compute the truncation error and stop when I see that adding a new term will not change the sum. This is not a good idea, not a good idea for many problems. I would like you, if you are interested in the the computation of the exponential to see this reference from Moller and Van Loon. They are two people very specialized in numerical algebra. One of them, Moller, I think he found a MATLAB. And this paper is very, very interesting because they present about 20 ways to compute the exponential of a matrix. And the conclusion of that is no one is good for every matrix. So it depends really on the matrix. If it's symmetric, if it is sparse or no, if you had to store the matrix or no, etc. Okay, so I will just two things. One of them, there are many methods, and the other thing is this is a good reference to read. So how can we go from scalar to matrix case? Okay, so we have an approximation. Suppose we have an approximation for the exponential in the complex plane, and you know that this approximation converges or decreases to zero very fast, but only in a region of the complex plane, call it lambda. Suppose this is lambda. And you know that in this region, your approximation is very good in the sense that it decreases geometrically or something like that. How can you extend it to the exponential? This is also general idea, you know, function on scalars, how to go to matrices. Here we, of course, for diagonal matrices, it's easy to define the approximation. But let's suppose that the approximation defined for matrix, and let's suppose this very important relation. Okay, Rn applied to PA, P minus 1 is just the approximation of A times P from left and P minus 1 at the end. If this is the case, it's very simple to generalize to your scalar approximation to matrix approximation. Just write exponential A minus its approximation. So this is exactly exponential A P D P minus 1 minus P approximation of D P minus 1. Okay, and okay, so this is less than the norm of P, the norm of P minus 1, and the norm of D minus R of D, the approximation of a diagonal matrix. Okay, so this is the condition number, and you get this bound of the error. So the error, when you approximate the exponential of a matrix, is just the error when you approximate its eigenvalues, but don't forget that you have to multiply by the condition number. So if A is a normal matrix, if it's a symmetric matrix, this condition number is 1, and things are really easier to. Yeah, we are in this case. If the matrix A is a Hermitian matrix or symmetric matrix, the error when you approximate it by rational approximation is just the same than the error you do when you approximate the spectrum of A in the complex plane. Okay, and this is what I mentioned here is very important for me. This is exactly what I'm interested in. My matrices will come from the discretization of the Laplacian, and will be in this favorable case. Okay, so how do I define the approximation of the exponential of matrix A? Very simple. You remember that for scalars, the approximation was this AK Z plus theta K from K from 1 to N. You just define this for matrices. Okay. So A plus theta K identity is it's okay. It's a regular matrix because we know that okay, if A is symmetric, so and we know that theta K will not be a real number for. Okay, what can we do very quickly? So in that case, the error is just the error when you approximate the spectrum of A. So let's go back here to see how this is very interesting. Okay, so I take a matrix, and instead of applying my rational approximation to to the scalar, I will apply it to the matrix. But if my matrix is the discretization of Laplacian, if its spectrum is negative, it means that the quality of the approximation of, oh, I'm sorry, I have a problem with my pen. The difference between the difference between A and exponential, the difference between A and exponential A and its rational approximation is just the exponential of Z minus the rational approximation of Z, where Z is an eigenvalue. Okay, so if you have a good approximation on the eigenvalues, you have a good approximation for the matrix. Okay, so we define the approximation of diagonal matrix this way. And let me show you some very briefly some application of this. First of all, I take a matrix with a spectrum in the half negative real axis, and I will I compute this error, and in this abscissa here you have. Here I put the dimension, so I want you to take to see how the dimension of the matrix will change the accuracy. And you see here that it doesn't change at all the accuracy. And this is why this is true. It is because all the spectrum of this finite difference approximation of A here is the finite difference approximation of the Laplacian in 1D. So if you fix n, let's say n equal 4, the spectrum is located somewhere here. But if you take a larger value of n, you just add some other value, and this will not affect the precision, because the accuracy, because you remember the shape of the error is this, and the maximum decrease is very, very fast, just to zero very fast. Okay? So if your spectrum, if you have good results with a spectrum located here, and you have a new matrix with a spectrum located here, this will not change anything. That's why you have almost straight lines. Okay, what about matrix exponential? No, sorry. Let me tell you here that, of course, if you increase n, you decrease the accuracy. Tell you that n is a kind of truncator. A from 1 to 1, ak a plus theta k I minus 1. So n is this. So I told you briefly in the introduction that the most important thing in numerical analysis is the computation of exponential a times v. How do you compute exponential a times v? So exponential a is approximated by this. This is exactly what is here with these vectors here, solution of this linear system. So this is absolutely the heart of the algorithm, the idea. What does it mean? This means that if you can compute every f, so what is the computational time? I call it CPU, maybe it's better to say computational time. What the computational time here to compute exponential a times v, what is it? It is the computational time to compute this sum, but you can compute in parallel this sum because each of these systems is independent from the others. So if you have n processors, you can compute each fkj on one processor and then collect them to compute exponential AV. Okay, so what is the cost? The cost of this, the cost of this of the computation of this is just the cost of solving one linear system, which is very, very cheap. Okay, so let's sorry, I have to let's say what do you obtain here? You can see much more detail on the preprint. So we compare with MATLAB function XM, and we obtain better results than MATLAB function XM. What you see here, all these plus symbols, signs, they are all of them. Each of them, sorry, is a value of n. I don't remember the value here, but let's say 4, 6, 8, etc. And they are all the same because let me precise again that if you can compute each of these each of these vectors independently from the other, you don't. The total time is just the time for computing one of them. Okay, so what I did here, I didn't really use parallel computing. I just compute one of them to see what it looks like. Okay, why this is useful for a differential equation? Let's go back to differential equation. U prime equal AU plus F, and you integrate it. You obtain this Duhamel's formula. And you see here that to compute U, it's useful to not only to compute exactly the exponential times U0, but also something, a kind of moment of the exponential. These are, you can write this as some exponential at sometimes t times do not precise what is here, it doesn't matter. It's a times something times I'm sorry, no, if f is polynomial, if f is polynomial, then this is just like I'm sorry, just like computing some exponential a times s to some power. Okay, something like that. So some moment. What I want to say that you have to compute the exponential, but also some integrals involving the exponentials. Okay, so and the goal, of course, is to design an efficient algorithm to compute the solution of this problem. Okay, so if the source term is polynomial, the solution is known explicitly in terms of some function called the phi functions. For example, there is the problem. I don't know if you hear me, but I So do I have to share again my screen? I don't know what happened.
You should share again. I don't know,
sorry.
it's like
Okay.
cut off.
Okay. So if I have to. So let's consider the case where you have just constant. F0 is a constant. In that case, the solution is given by this function. And if you add constant plus a linear term, you just had to add this new term, the new operator, psi2, etc. So why this is important? This is important because not only, it's not important because in real situation, your f is, your source term is polynomial, but it's important because when you have to deal with nonlinear problems, you should make some discretization. And at between time tm and tm plus 1, you can suppose that your function is well approximated by a constant or by a linear function or quadratic, but no more. You don't need to have more. Okay, so if you consider that between tm and tm plus 1, your function is constant, you have an exact solution of the equation. If it's linear, you have also an explicit form, which depends this time from psi2. Okay. So what are these functions are called the phi function? They have many different equivalent definition. I used the explicit one. You can find in the literature many of them: recurrence relation, series, integrals, etc. I used this as a definition, and I will use this to define the phi function for matrices. But in many, okay, you can find all the definitions. So I gave here in good reference for the exponential integrator. So for matrices, how do you define phi g for matrices? We choose to define it phi g of A using the series, which is a convergent series, and it's easy to see this relation, to prove this relation, and also to see this very fine relation, which is very close. Remember that the rational approximation has this property. Okay. And the idea now, sorry, the question now is how to approximate this RG. Okay. I don't have time to precise to give too much detail because you have to stop in 10 minutes or even less than 10 minutes. So let me define, this is a definition of R and G. In terms of Rn0, what is Rn0? Rn0 is the previous, what I called before, Rn, when I had to approximate only the exponential. Remember also that the exponential is just phi 0 of A. Now I want to compute, to approximate all this phi g, and I defined Rn this way, exactly like, remember how phi g was defined? One of the definition of phi g is this: exponential z minus the truncated series at g minus 1. Okay, you do the same, you get a good simple recurrence relation, and we can prove, it's easy to prove that Rn is an approximation of phi g at the origin. It's not a Paddy approximation, but it's an approximation at the origin, and this is exactly it look like what we saw, what you said about Rn0. So RNG has the same kind of properties as RNG, but I'm sorry, there is again a problem. I don't really know why. Let me check something. I don't want to stop before showing you some examples and application. So I maybe go directly to the numerical examples. But what was the idea? The idea is, you know that if the right-hand side is a polynomial, the solution is explicitly known as a linear as a combination of the phi function. So if you can define some approximation of this phi function, so these phi functions, you get a numerical approximation of the solution. Okay. Okay, see if the problem comes from my tablet, I will connect from the computer. I will not be able to write on the tablet, but I could probably okay. Let me now, sorry. Okay. Okay, so, sorry. So the problem maybe comes from my tablet. So now I cannot write anything, but you can see my slides. So let me just show you the main idea. I'm sorry. So here, here you know the exact solution, and the idea is just to replace this phi j by some approximation of this phi j, and we define this approximation here. The last thing I said before this problem. Okay, so if f is constant, this is the exact solution. And what is the approximation? Very easy. This is the exponential. We know how to approximate it. This is phi 1, and I approximate it by the rational approximation I give. Okay, and the cost, computational time, if we can use parallel computing, is just the computational time of one linear system. So I will not show all the examples, but go to the most important one, maybe this one. So here we consider the two-dimensional heat equation on a square in the plane with directly boundary condition. And the initial value, yes, is an eigenfunction of the Laplacian. Sorry, yes, the initial value where is an eigenvalue, is an eigenfunction, and the source term is also up to a constant, another eigenfunction of the Laplacian with this condition. It's a classical you start from something that have three oscillation in one direction and two in one direction, and you know that asymptotically the solution goes to a function that have two oscillation in the first direction and three in the other. So you go from 2 and 3 to 3 and 2, something like that. Okay, so this is the exact solution, and yes, I will just show you this result. Sorry. So here we compare our method for solving this 2D problem with two implicit solvers, BDF solver and the Radau solver. Okay. BDF is the background differentiation formula. They are well-known implicit solver, very precise, but also, of course, expensive. And we use the solvers available in Python. What is SciPy in Python module, in the module SciPy, and we use the solve IVP procedure of function. Okay, so here we have work precision diagrams. What is this? You have here the computational time, and here the error. All these symbols here are related to our rational approximation for n equal 4, 8, etc. And you see that as n increases, the solution decreases. Here, this star is for n equal 32. It seems larger than the other, but it doesn't matter because all these are very small. This is the zero of the computations. Compare it to the BDF, the background differential formula in blue here, or to the Radau in green, and you see that. So we consider two times. That's important. T equal 1 on the right hand side. T equal 1 is the asymptotic times. So we go from 3 times 2 period to 2 times 3 periods. Okay, so in the solution will not really not stationary, but almost stationary. It goes asymptotically to this solution. And on the left, you have time t is 0.01, which is a transitory time, which is more, the structure of the solution is more complicated. So if you compare here, you see that our method is less, it took less time than the two other solvers. I will give you the precise ratio in a moment. You see also here on the right that also on the left that Radau is very, very accurate. Sorry. Why do I have put here 5 value for each of these solvers? Because there is a parameter in when you use these solvers, you can use the default parameters or define yourself the parameters. So I run the programs using the default parameters, and the result was not very good. And I changed the default parameter to give a smaller parameter. They call them A-tol and E-tol or something like that. It's kind of tolerance. I take them very small to get the best accuracy possible. And what we can see, let me check my notes. Let's see here on the right, which is the less favorable case for us. Comparing to the BDF, we have a speedup of 30. Speedup is the ratio between computational time for BDF and computational for our method. To get the same precision, it took 16, our method is 16 times 16 faster. For Radau, you see here these two terms, these two values here. To get the accuracy we obtain with n equal 32, it took a very long time for Radau to achieve it, and BDF wasn't able to achieve it unless I put a more restrictive tolerance values, which will, and computation will take too long. Okay, so in this case, the speed was about 154. So this is the difference between this point and this one is very important. Okay, so no, this is we do also something with finite element. It's not very important. I will just conclude now. So we have a simple method which is based on very old idea. It's very simple, but it gives a nice result in especially in the computation of exponential A times V, which is what we need in numerical algorithm solving the differential equation. And also there is something very important. We don't have to store the dense matrices, but only to compute the matrix A. Because even if matrix A is sparse, its exponential is dense. So if you have a method that computes the exponential, which is do not require to store the matrices, this is very okay. And of course, there's a lot to do. We will see how it behaves for the wave equation, and also, first of all, for nonlinear equation. We didn't handle a nonlinear equation right now, and I will stop here and thank you again for your attention.
All right, thank you very much, Sidi. Thank you so much for the nice talk, giving a bit of the introduction as well. Please, for those online, I'll let you ask your questions if you have.
Please.
So if you have a question, please go ahead.
I do have a question. May I?
Yes, please. Yes, please.
Go ahead.
One is a curiosity. That error estimate you show in the beginning, do you have any information regarding relative error? Or just the...
Okay, this is a very good question because I look at a lot of paper on this kind of work. So okay, let me just check my note if it's, so the problem is the following. If you take the case of this matrix coming from the discretization of the relation, if the L2 norm of the matrix is very small, if you change the dimension, you just have to look at the largest eigenvalue of the matrix. And to be honest, I don't know if what I show you right now is the let me just check it if this relative error or not. So one second, please. I will say this is a relative error, but it's very recent. The last yes, it's a relative error, but I didn't know why sometimes in the people consider the absolute error or relative error. I will say absolute error, relative error makes sense if you have to compute something that is very huge, because it doesn't make sense to approximate very accurately something that is very, very huge. But if you approximate something that is very small, maybe absolute error is better. But I don't know. I'm open to any suggestion on this. It's really a question I'm asking myself, what's the best to do? Except these two extreme cases. For something very large, use relative errors. For something very, very small, use absolute errors. But I don't know what's the good way to present results. Of course, we compare. In the preprint, we compare with other results, except mainly for result. We compare with people using the Krylov method or something like that. But I didn't talk about this here.
Okay, thank you.
Thank you for the question. Yeah, it's really an important question because what's the good comparison of these things? I don't know. And also, I'm quite new in this area, and so I saw a lot of paper, and sometimes they use the absolute error and sometimes the relative.
Okay, thank you.
Thank you for your interest and comment. Okay, so I hope to see you. Yeah, I hope to see you in Ghana next year for our.
Also, I think Alexander is from Brazil, or if I'm right.
Okay. So we stop now, or you stop the recording. I have just a question for you.
Yes. I stopped the recording now.